Welcome, my dear students. In the previous lecture, we have established that B of xy is a normed space. Now, in this lecture, we will be establishing the criteria for B of xy to be a Banach space. So, the completeness of B of xy. So, let me state the theorem. So, theorem states that if y is a Banach space, then B of xy is a Banach space. So, in order to become the set of all bounded linear operators from x to y, where x and y are normed spaces, to be complete, it is enough that the space y should be complete. So, even if x is not complete, even the range space y is complete, then the space of all bounded linear operators from x to y is also complete. So, in order to prove this, we have to consider an arbitrary Cauchy sequence from P of xy, and we have to prove that its limit should also be in B of xy. That's what we are going to prove. So, consider an arbitrary Cauchy sequence of bounded linear operators. Operators from x to y. So, which is Tn. So, Tn are set of all collection of bounded linear operator from a normed space x onto a Banach space y. And we will prove that there exists a bounded linear operator T such that Tn converges to T and T belongs to B of xy. So T is bounded linear operator. Okay, this is what we are going to prove. Actually, we have to construct this T. So for every x element in capital X, we have to associate that with a y in capital Y, and associated with that, we have to define an operator T and prove that our Tn converges to T and T is bounded and T is as well as linear. Okay, so we have assumed that Tn is Cauchy. So since Tn is Cauchy, by the condition of Cauchy sequence, we can write it as norm of Tn minus Tm should be less than epsilon for all m comma n greater than or equal to capital. For every epsilon greater than 0, there exists an for every epsilon greater than 0, there exists a n such that norm of Tn minus Tm should be less than epsilon for all m comma n greater than capital N. Okay, and this is true for all x. So for all x element of capital X. Now, if you apply x on this, norm of Tn minus Tm of x should be equal to norm of Tnx minus Tmx, which is norm of Tnx minus Tmx should be equal to norm of Tn minus Tmx by definition, and this should be less than or equal to norm of Tn minus Tm times norm x, because Tn is a bounded linear operator, Tm is a bounded linear operator, then Tn minus Tm is also a bounded linear operator. Okay. So by the definition of bounded linear operators, this should be less than or equal to norm of Tn minus Tm times norm x. Now Tn minus Tm is less than epsilon for all m comma n greater than capital N. So this should be less than epsilon times norm x for all m comma n greater than capital. Now this is true for every x. That is, we have established that norm of Tnx minus Tmx should be less than or equal to, actually less than epsilon for all epsilon times norm x for all m comma n greater than capital X and for all x element of capital X. So we choose a particular x. So for a fixed x, we choose a particular x element of capital X, and associated with that we must have a epsilon x such that where epsilon x is actually same as epsilon, such that epsilon x times norm x should be less than some epsilon tilde. Okay, so we can choose for the fixed x, we can choose an epsilon tilde such that epsilon x times norm x should be less than epsilon tilde. Okay, we are choosing epsilon as epsilon x because we are fixing this x. This result is true for every x. So for a particular x, we are choosing associated with that x, we are taking epsilon x to be an epsilon by fixing a particular x. So now we can write our equation. This is equation number 1 as norm of Tnx minus Tmx should be less than epsilon x times norm x, which is less than epsilon tilde for all m comma n greater than capital N. So norm of Tnx minus Tmx should be less than epsilon tilde for all m comma n greater than capital N, which means that this is true for a particular x, which means that this sequence Tnx, the sequence Tnx is actually Cauchy. Now Tnx is a sequence which is in Y, and Y is complete. Y is Banach or complete, which means every Cauchy sequence in Y converges in Y itself. So Tnx, the sequence Tnx, converges to some Y which belongs to capital Y, because Tnx is a Cauchy sequence in capital Y and Y is a complete space. Now we have fixed a particular x element of x, and associated with that we have found a y element of y, which is actually the limit of Tnx. Now associated with this x we can find a y. Now relate this x to y. Now associated with these two elements, for each x in capital X we can find a y in capital Y such that Tnx converges to some y. Now define associated with these two, define a map T from x to y, defined as Tx is equal to y. or limit n tends to infinity Tnx. This is what T is. So we have defined a map from x to y. For each x in capital X, we can take the limit of Tnx, where Tn is an arbitrary Cauchy sequence which is defined on B of xy as y. Now we have related a particular x, every x in capital X onto some y in capital Y, and associated with that, we have defined a map T from x to y using this definition. So we have found a map T from x to y. Now we have to prove that T is actually an element in B of xy. For that, we have to prove that T is a bounded operator, T is a linear operator, and also Tn converges to T. So, we are going to prove that T element of B of xy and Tn converges to T. These are the things which we are going to prove. So, Tn is a Cauchy sequence which converges to some T and T element of B of xy. So, which means that every Cauchy sequence converges in B of xy, which means B of xy is complete. So, the first thing is T element of B of xy. In order to prove that, first we have to prove that T is linear. So, T of some alpha x plus some beta y, which by definition is equal to limit n tends to infinity Tn of alpha x plus beta y. Since Tn is a linear operator from x to y, by linearity property, we can write it as this should be equal to limit n tends to infinity alpha times Tnx plus beta times Tny, since Tn is linear. Now, splitting the limits, we get alpha times limit n tends to infinity Tnx plus beta times limit n tends to infinity Tny. Now, limit n tends to infinity Tnx is taken to be Tx, and limit n tends to infinity Tny is taken to be Ty. It should be equal to alpha Tx plus beta Ty. So, which means that T of alpha x plus beta y is equal to alpha Tx plus beta Ty. So, which means that T is linear. So, T is linear and T is from x to y. Next, we will prove that T is linear. T is bounded. So, we do not prove this directly. We prove the fact that Tn minus T is bounded, or T minus Tn is actually bounded. That's what we are going to prove. Or Tn minus T is bounded. So, we will prove that Tn minus T is bounded. So, Tn minus T is bounded, and we already know that Tn is bounded. So, the difference of two bounded linear operators is again bounded. So, Tn minus T becomes bounded, which is actually T. So, which implies T is bounded. So, in order to prove that T is bounded, it is enough to prove that Tn minus T is bounded. So, for that, we will establish, we have already established that norm of Tnx minus Tmx should be less than S epsilon times norm x for all m comma n greater than capital N. So, which means that our sequence Tnx is actually Cauchy for a fixed x. Now, for m greater than n, this sequence Tnx converges to some Tx. Because it's a Cauchy sequence in capital Y, it should be converges to some point. That point is taken to be Tx or Y. Okay. So as m tends to infinity, Tmx tends to T of x, which is what we have taken. Now, norm of Tnx minus T of x should be equal to norm of Tnx minus limit m tends to infinity T of x, Tmx. We can use this because of the continuity of the norm. If xn converges to x, then norm xn also converges to norm x. We have already established this. Now, we can take the limit outside, and here it is n. N is independent of m, so you can take the limit outside. So this should be equal to limit m tends to infinity norm of Tnx minus Tmx. Okay. So we have already established that norm of Tnx minus Tmx is less than epsilon into norm x. So this should be less than limit m tends to infinity epsilon. So which is equal to epsilon times norm x. So we have proved that norm of Tnx minus T of x should be less than epsilon times norm x. Where n also greater than capital N. M is taken to be greater than capital N. To apply this, m and n should be greater than capital N. Okay. So this means that this can be written as norm of Tn minus T of x should be less than epsilon times norm x. If we take C as epsilon, this means that norm of Tn minus T of x is less than or equal to C into norm x, which means that Tn minus T is bounded by the definition of boundedness. So Tn minus T is bounded. We have established that. So Tn minus T is bounded where n should be greater than some capital N. Now T can be written as Tn minus Tn minus T. So which here Tn is bounded. We have proved that this is also bounded. The difference of two bounded linear operators is again a bounded linear operator. So which means that T is bounded. So in order to prove that T is bounded, we have first proved that Tn minus T is bounded, and Tn is assumed to be a bounded operators by taking Tn as a Cauchy sequence in B of xy. So T can be written as Tn minus T, the difference of two bounded operators, which is again bounded. So T is assumed to be bounded. Now the thing which remains to prove is the fact that Tn converges to T. So T is actually what we have established, that T is actually bounded linear and T from x to y. So which means that T element of B of xy. So first part is done. Next we have to prove that Tn converges to T. Okay. Or norm of Tn minus T tends to 0 as n tends to infinity. Which can be established trivially from this. We have established that norm of Tn minus t of x should be less than or equal to, actually less than epsilon times norm x for all n greater than some capital N. So if you move this norm x onto the left hand side, so norm of Tn minus t of x by norm x should be less than epsilon for all n greater than capital N. Now this value is less than epsilon, then its supremum is also less than epsilon. Now take supremum x element of d of t and x norm x is equal to 1 or x not equal to 0, both norm of Tn minus t of x by norm x is 1. This should be less than epsilon if we take norm x to be 1. Or in other words, we can write, since this quantity is less than epsilon for all n greater than n, if we take supremum x element of d of t, x not equal to 0, norm of Tn minus t of x by norm x should be less than epsilon, because each of this part is less than epsilon for all n greater than capital. This is actually the definition of norm of Tn minus t. Okay. So this, from this we can easily write the left hand side is actually norm of Tn minus t. Norm of Tn minus t is less than epsilon for all n greater than n, which is the definition of convergence, which means that Tn converges to t. So we have taken an arbitrary Cauchy sequence Tn. We have proved that Tn converges to t and t is an element in B of xy. So every Cauchy sequence converges. So every Cauchy sequence in B of xy converges, which means that B of xy is actually complete. So whenever y is complete, B of xy is also complete. The completeness of y is essential because using that fact only we can connect this by this epsilon. Norm of Tnx minus Tmx can be converges to some y. This y part, Tmx converges to some y. This is established only by the completion of y. Here, this Tx is Cauchy, then it should converge to some y. So that y exists only when capital Y is complete. So it is an essential part of the theorem. Thank you.